Okay, hello everyone. My name is Cheng Duan. I'm from University of Ottawa, and today I will introduce this paper, the K-Closest Resemblance Classifier for remote sensing datasets. Um, I wrote this paper with Dr. Nabil from National Research Council and Professor Diana from University of Ottawa. So I will first introduce what exactly is the K-Closest Resemblance Classifier. So we know there are several powerful supervised learning algorithms there. They can work pretty well on handling hand-dimensional data. They can map classes with complex characteristics, but there's obviously some limitations for them as well. So like for deep learning, they have a problem with the knowledge interpretation. Basically, if you use a deep learning, you can't really tell how this model produce the answers for you. Um, Another problem is they sometimes works not well on the imbalanced datasets. So the Dr. Nabil comes up with this K-Closest Resemblance Classifier, the KCR. It is a prototype-based classifier. It works by first select the smallest possible subset of prototypes. So when there's a new sample S comes, you use this set of prototypes to decide which class this sample will be assigned to. So it is based on the social choice theory and preference modeling. It has several benefits. So you don't need to normalize the features, and during the learning you won't lose any information because you will use all the values from all the features for the training steps. So before the actual working procedure of the KCR, there are two key concepts we need to understand first. So performance matrix and the absolute distance. So this matrix here, each component of it corresponds to the absolute distance between the sample S to be assigned and the prototype of the class according to the attribute or the feature GG. So each class is represented by one or several prototypes. And this distance here, we use this equation to calculate our absolute distance. So first look at this second member here. So it used the value of the left boundary of the interval to minus the value of the attribute of the sample S. For this third member here, we use the value of the G's attribute of sample S to minus the right boundary, the value of the right boundary of that same interval. And then we use these two values and the 0, we compare them, and we use the maximum value of these three as the distance. So this interval here I mentioned, I will introduce it later in this presentation. So after we understand these two key concepts, the actual working procedure of KCR includes two steps. The first one is the learning phase. For each class C, the KCR will determine a set of prototypes from the training set. So these prototypes are actually learns the data representation of each class. And for each prototype and each feature of each class, there will be an interval there. So this interval is the same one I mentioned during the absolute distance calculation. And then we move to the second step, the classification. So this step, we're trying to classify a sample S to a class. So the first step is to calculate the R-ranking relations. So we know there's a prototype BH, a prototype BL, they from class CH and CL respectively, and we want to know which prototype fits to this new sample S better. So this is the means of the P. So because we know there are a lot of prototypes being produced, so we will have PS means the R-ranking relation for all the possible pairs of the prototypes. So after we have PS, we move to the scoring function step. We select the best P among that list of P's. So after we know the best P, we know the best prototype that fits to this new sample S, then we can say this new sample S belongs to the same class as that best prototype. So that's how the KCR works. So in this paper, we used a remote sensing dataset from the University of California. It is created based on the high-resolution geographical images. So in this dataset, each instance had 147 features. There are 9 classes, and there are 168 data for training, 507 for testing. So the interesting thing here is if we look at the soil or pool, there are only have 29 data or 34 data for it. But if you look at the classes like concrete or grass, they have more than 100 data in those classes. So this is a imbalanced data size. So in our experiments, we compare the performance of the KCR with the random forest, SVM, KN, and multi-layer perceptron. We train and validation these classifiers on using the Cheng cross validation, and this table here shows all the F1 scores all the F1 scores we got. It is quite obvious that KCR outperforms all the other classifiers, and it's more interesting to say like for class soil here. This class soil has much less number of data in the dataset, but it still got 0.88 F1 score. It's almost the same as other classes here in this KCR column. But if you look at the other classifiers, the 0.67 is much worse than the other classes. Same for 0.4 here, 0.09, 0.21. So this result here means the KCR actually works quite well on the imbalanced dataset, even with the class with less number of data in the dataset. So this picture here, this shows the ROC curves. So you can see all the curves for all the classes, they actually overlaps with each other. So this we are trying to visually show you that KCR actually works on imbalanced dataset. It does not bias on any particular class that with more data in the datasets. So in the future, we actually plans to apply KCR on some natural language processing tasks like depression detection. Also, we need to improve the running time because currently it uses quite a long time to train and predict the instances. So that's it for this presentation. If you could learn more details in our paper, if you got any questions, of course you can email the authors, you can email us, and thank you for listening.